Oke, selamat siang rekan-rekan semua. Hari ini kita kedatangan Profesor Akbar Rhamdhani ya dari Swinburne University of Technology. Nanti presentasi akan dilaksanakan dalam bahasa Inggris. Namun kalau kalian mau punya pertanyaan dalam bahasa Indonesia juga sangat-sangat welcome ya. Okay, so Professor Akbar Rhamdhani is my supervisor. He supervised me when I did the PhD ketika saya S3 dulu, and he's now the professor at Swinburne University of Technology in Melbourne, Australia. So Professor Akbar, please give your time is yours. Thank you.
Thank you, Bu Winnie. Good afternoon, everyone. It's a pleasure for me to be here today to speak with you, to give you some explain about some of the things that I actually lecture. So this material I lectured this material to master's students, master's sort of program at Swinburne. So, and there's a portion of these materials that's quite relevant to metallurgy in general about recycling. So so I'm going to talk about that one. So so let me just first of all, because I'm going to show the slide in my screen, so I couldn't see the chat room or anything. So if there's anything from you, if you have any question, just feel free to interrupt me. Yeah, don't hesitate to do that. Don't worry. The fact that we have quite a small class here is actually pretty good, because we can actually be focused more on discussion, right? So if you have any inquiries or anything, just feel free to interrupt me, and then we can stop, and then we can clarify that concept a bit better, for example. Right, so let me just share my screen. It's good. Right, let me just put that into small view. Okay, so the material that I'm going to talk about this afternoon is about recycling of urban ores and complex products, right? So this, as I said, is a part of materials that I lectured at the master's level here at Swinburne. It started with some general information, then we go into more details and specific as we go along. I think the reason why I want to explain about this one is the fact that currently all over the world, there's a push in trying to process urban ores and complex products, and the expertise of chemical engineering as well as metallurgical engineering in particular are vital for the success of these processes. So you can see a bit later how you later on can play a significant role in for example, developing new process or improving the current process for this urban ores processing. Yeah. So right. So maybe I'll just explain a bit about my research area and also research directions. So there are in general 4 research directions that I'm currently focusing on. The first one is urban ores processing and metals recycling. So this is the one that quite relevant with the current presentation, current sort of lecture. So we have a number of projects and also research in this area. For example, we try to develop a waste recycling system, trying to understand what is the best system in a particular country, including Indonesia. We have a project on novel refining process for recycling of solar panel, right? Photovoltaic cell, and also recycling of alkaline and lithium-ion batteries. and also permanent magnet, right? So these are some of the area that we are working on in this urban ores processing and metals recycling. The other thing is also we focus also on solar metallurgy. So we are using solar energy, yeah, to process metals and minerals, right? So several projects include, solar assisted small scale recycling of alkaline batteries, solar carbon reduction of spent lithium-ion batteries from electric vehicle, solar dephosphorylation and cracking of monazite, solar processing of ilmenite ores, and also solar processing of iron ores, right? So I should mention, solar energy, if you really sort of concentrate it, focus into one spot, it actually can be, it can actually get quite a high temperature. Yeah, so it can go up to thousands of degrees of Celsius. Now, for example, in Swinburne, we have this solar simulator. We have 7 lamps, that high-powered lamp. Each of that is about 6,000 watt, and we focus that into a furnace, and we use that sort of heat to process metals and minerals. So the one on the right, for example, is some results on ilmenite processing using a solar simulator, and actually this rig, this experimental apparatus, it can reach up to 2,000 degrees Celsius. Yeah. I'm also focused on decarbonization of metals and also minerals processes. Trying to use hydrogen to process metals, and process or recycling of batteries with hydrogen reduction, and also iron ore reduction using hydrogen. And the other quite interesting things that we are doing is, we call it astrometallurgy, right, or extraterrestrial metals processing. So in this case, we're trying to develop minerals and metals processing for the application of extraterrestrial. If you want to make something moon, and also in Mars, and so on. Right? So there are also a number of processes that we are, and project that we currently carry out in our group here in Swinburne. So that's give you the area of my research, and also give you some flavor of it. But in the context of this lecture, number one is the area of number one is the one that is very related there. So now let's go into the lecture itself. So in this week, tonight, or this afternoon, and also next week, I'm going to talk about recycling in general, and also recycling of in general, like materials, and also recycling of complex products such as cars, and also electronics. So in this case, electronic waste. Yeah. So I'm going to start with something that is the concept, some of the terminology, the ideas of recycling itself, and then go into the details about, if we're talking about simple materials such as metals, glass, and then construction materials, what are the approach that we use to recycle this one, and lastly, we're going into details about more complex product, what's the approach that we're taking in that situation there. Yeah. So talking about recycling, I think we need to start with some definition and terms and concepts. Simple terms and simple concepts. Here, just talk about the materials and material cycle first. So straightforward materials. Materials are substances used by humans to create products or goods, right? So the original substance, we call that the materials, right? And products or goods basically consists of structures. It can be buildings, dams, roads, and other stuff, right? Vehicles can be cars, trains, ships, and aeroplane, and so on. It is it is something that we use for our sort of daily life application, right? Starting from a small scale into a big scale. It can be a technical products or goods, it can be arts or other subject, right? And we can, of course, classify materials depends on a number of things. We can classify materials based on their nature, such as aggregates, metals, alloys, ceramics, fibers, composite materials, wood, and whatever. But we can also specify materials and classify them based on their application, right? Nuclear materials, optical materials, dental materials, smart materials, and other stuff, right? So I think just from looking at the words, you can sort of guess, okay, this is actually for these applications, and you can see what sort of the base materials involved in there. So ultimately, all materials coming from Earth, yeah? So from the Earth's crust and also the biosphere. So you can see the picture on the left, the structure of the Earth. So mainly we're taking all of these materials from the crust, right? Which is between 0 and surface down to 35 kilometers. In some case, probably go beyond that one. Maybe not. Most it's basically within the crust itself. I think more than 35 kilometers is not really, practical there. So the crust and the biosphere. So in this case, there's a terms of biosphere. So biosphere in general is basically the region of the surface of the Earth, including the atmosphere, where occupied by living things, living organisms, right, including humans, right? So we're taking stuff from the biosphere and also the crust of the Earth, right? So shortly speaking, we have limited resources, right? Because it's Earth, right? It's of course, from time to time we can get some object coming from outer space, but in general, the majority of the materials is basically the Earth itself. So it's a limited resources. Yeah. So the way we do things here is that we try to get the materials from the Earth, and then we process them, right? And we in this sort of process we call this material cycle. So we can see from here, if we start from the Earth's crust and biosphere, this blue circle, we mine them, we drill them to get some materials, to get some oil, gas, and harvest them, and we get this oil, coal, gas, ores, sand, rocks, wood, plants, and etc. Right? And we call that raw materials. Then we further process these materials. We extract them, we refine them, and of course we process them to get to what is called basic materials. That can be metals, chemicals, paper, cement, and fibers, and other stuff as well. Then we process this further to make what is called engineering materials. So that includes alloys, ceramics, plastics, concrete, textiles, and other engineering materials, right? So that's just still halfway. So it's not a product yet. So then we use different types of design, manufacturing, and assembly processes to develop products, devices, machines, structures, works of arts, and other stuff. Right? So these are the products that we use every day, and then we use them. There's a performance of these products and devices. We surface them, we use them, and up to a point where everything's basically all these products basically dies, and it comes to their end of life, right? So at the end of life, we usually dispose them, yeah, either through landfilling or storage them, or also combust them, right? And that goes back into the Earth's crust and biosphere, right? So this is called the material cycle, right? And here, just a comment here, when we're talking about basic materials here, this is what is called primary materials and also secondary materials. So secondary materials, in this case, is basically recycled materials. Yeah. Now, the thing that I want to mention in here is that, okay, we have this material cycle, yeah, but we can sort of do an intervention before the end of life products goes into a disposal stage, right? So at this sort of pink circle, we can do remanufacturing, for example, to make new products, devices, and machines, and so on. We can reuse if it's still usable, yeah? Or we can recycle them. Now, the recycle itself can also go back into basic materials. We try to break it down and then retrieve and extract the original metals or the original chemicals, the original materials, in this case, paper, cement, whatever. Or we can sort of recycle back into this step here where we get the engineering materials, right, rather than a very basic material step. So it will depend on what the products and also the states of that products, yeah? Whether it's still good or bad or so on. So there are some terms from the previous cycle there. So we use the terms recycling, which is basically the introduction of recovered materials into the material cycle. Yeah. So this one here. There's also reuse. There's the use of product or component more than once, either for its original function or for a different function, right? And also remanufacturing. Remanufacturing means it's repairing and also overhaul of some parts, components, equipment, machines, to meet the same or similar specification as new, right? So the examples of these terms can be seen on the right-hand side here. Of course, recycling, you can go up to its basic materials. You get the metals back. You remelt the glasses and get the glasses back, and so on. Sorry. In terms of reuse, for example, it can be, example here is glass bottles. It can be collected, washed, and refilled. The old Coca-Cola bottles, for example, for example, here in Australia, if you want to do barbecuing, we usually buy the gas in a cylinder that from a store, and then we buy it. And then once it's finished, the cylinder, gas cylinder, can be reused. So we basically return it back, and then they can refill that one, and then we can reuse the bottle itself. Remanufacturing, any products or any machines, car, truck, car engine and truck engines, jet engines, printer cartridge, aircraft, and so on. So we repair, or we do a little bit of manufacturing process, do a surface treatment, fix the surface, so that it can be reused as a new sort of component or products. Yeah. So that's the material cycle, and also the recycle, reuse, and remanufacture, the 3R, right? And speaking of these material cycles, in this process, in each of this process, 99.9%, you will produce waste. Yeah. So, for example, here, when you dispose the end-of-life products into the Earth's crust and biosphere, it involves some waste. During the mining, drilling, it involves some waste. During the production of basic materials, for example, extraction, refining process, you produce waste. During the process of manufacturing, you produce waste, right? So it's very difficult to really goes into zero waste. We try to do that, but you know, it's only a special situation when we can really go into zero waste. Yeah. So there are two broad categories of waste or potential waste. We can say that the end-of-life products here, we can call that as waste as well. We can use that for recycle, reuse, and manufacture, and also waste from the others, primary production and also manufacturing. Yeah. So speaking about waste, so waste can be quite useful as well. Waste can be quite waste can still have some economical value, right? Waste can be can benefit us as well, yeah, to some extent. But we have to deal with that in a certain way. We have to process that in a certain way. So the conventional definition of waste is a thing or a substance that has been discarded and eventually sent to landfill or other disposal site, yeah, for storage or for combustion. Now, usually we store this waste if it's if it's radioactive, or if it contains highly toxic substances. So we basically secure it in a secure place so that it sort of leach to the environment, or there's some sort of emission with time with the environment. So we clearly store it in a secure facilities or secure sort of place to make sure that it contained. Yeah. In some case, there's also combustion. So, for example, waste, paper waste, plastics waste, tires waste, we can also get some value busting them, and that's also what usually done for these types of waste or materials. Now, there's also a better definition of waste, which is a thing or substance that has no purpose, right? Or because it has fulfilled its purpose, or it is not usable for its intended purpose, or it was not used for its intended purpose, right? So this implies that waste may be turned into non-waste. It's still value there. Yeah? We can reuse, remanufacture, and recycle of this waste. So now you probably also come across this term as well, circular economy. It's quite an important concept, and it's something that we strive for these days. So it is an economic system that aims to eliminate waste. We try to reduce the waste to zero, and we also try to continue to use the same resources if it's all possible, right? So it's basically resource efficient as well. Yeah. So how that sort of apply to this circular economy, right? Sorry, to this basic material cycle, right? So basically, what we want to do in here is we want to use this waste, and then we want to process them. And also, this waste, the end-of-life product, can also be termed as waste, including these end-of-life products. You want to use them, right? Either to recycle, reuse, and then manufacture. So basically, we're trying to remove the left part of this material cycle, so that we just sort of do this, right? So that's the idea of circular economy. Okay. And yeah, I should mention it is not easy. So circular economy is an aspiration, right? And a completely circular economy is not possible, since some waste is always associated with recycling, reusing, and remanufacturing. So, so actually things cannot be really fully circular, right? But we can strive towards that ideal condition. Yeah. Right. So we will discuss this later in more detail, but again, I want to put emphasis in here that metallurgy, including chemical engineering, and recycling, these are one of the key drivers in circular economy, right? So, so this is sort of a similar material cycle with a bit more information in it. Yeah? So in here, if we look at, we get some stuff or some materials from Earth's crust, so geological mine, and then we make a product. So that's already almost half of the material cycle. Then we use the products and we process the products, the end-of-life products, right? So we're creating this new cycle here where we process, we call it urban mining. So we take end-of-life products. In this case, this example is lamps and other sort of electronic waste and other electronic products. And then we collect them, dismantle, shredding, and we do a process, physical processes and also metallurgical processes to get the value back, to get the metals back, and to make a new product and also materials, right? So in here, this example here actually clearly shows the importance of metallurgy and also chemical engineering to support this circular economy and resource efficiency. Yeah. So again, I strongly believe that starting from now and in the future, you can play a significant role in trying to improve these processes, for example, or improve the circular economy and also resource efficiency in the context of the like something like this, for example. Right. Now, talking about the itself, so recycling is is trying to use waste, right? But there's a hierarchy of waste, right? We look at this earlier. The conventional hierarchy is that we can start with reduce the waste, and then reuse and remanufacture and recycle, right? So actually, going down, we have an increase. So a decrease in the desirability, right? So recycling is good, but that may not be the first choice, or that shouldn't be the first choice, right? So based on this conventional hierarchy, it's better to reduce first, and then reuse, and then remanufacture before we actually do the recycling, right? In here, the focus is not really on the reduction and or minimization of waste, but rather to eliminate the waste, right? Now, there's a new hierarchy, which I actually prefer. So in this case, the current sort of international, agreement is that focusing on elimination of waste at the source, right, rather than reducing the waste itself, right? So this is from the European Parliament Directive 2008/98/C, which sort of revises a bit on proposed sort of slightly different waste hierarchy. So first is prevention, right? And then second is the preparation for reuse and remanufacture. So this includes collection, sorting, dismantling, and so on. And then the recycling itself, yeah, which includes separation of materials and also reprocessing. And after that, there's also additional recovery. For example, if you want to recover the energy through some combustion, then you can get energy from waste or something, and so on. And the last bit is the disposal, where you actually landfill and also store some of this waste. Yeah. So going down, you're also decreasing the desirability in there. Now, recycling also is, again, it's not the first choice in here, but at least, you can see that the other up on the chain is one that we need to strive for, if possible, before you go into recycling. So that's why also around the world, there's also a greater emphasis on design of a product, a better design of a product, right? Design for sustainability. The reason is you want to make sure that things we make, things that we produce, it's easy to be recycled, easy to be processed afterwards, right? And it's we use it, or we make the products in a way so that it's energy efficient, and also not wasting a lot of resources, and so on, right? So here there are a number of things that I have mentioned. In a way, when we want to design something in a sustainable way, it means that the product should be designed for optimum use, right? From a number of angles, of course, in terms of the life of the product itself, the design, the materials. Only the most appropriate materials should be used. The smallest amount of quantities of materials should be used, just the exact amount, right? So not excessive use of materials. The products should be produced in environmentally friendly ways, reduce energy, water consumption, minimal emissions, smallest possible quantity of leftover materials also. And like I mentioned earlier, the products should also be designed so that they can be easily repaired, refurbished, and reused. For example, you will see that now the current LED TV, whatever, it has all the electronics is put on one side, right? And when you try to break them, trying to put them into, for example, a crushing machine to resize the waste there, it will easily broken. It will easily separated, right? So instead of using, for example, a glue or to fix them together, or using, let's say, it's basically like a clip-on, so it's easy to be separated. So, and there has been a lot of emphasis on that sort of these days. Yeah. So, just quick comment in here to support the strategy number 5 there. So, systems should be provided for collecting used products, right? So we need to have quite a good system for example, collecting cell phone and offline cell phone electronics. It will help. It will help in getting the materials back, and also so that's half the battle, because collection can be quite expensive as well. so on. Second one is the commissioning infrastructure, and also a system for separating and pre-sorting materials before reusing or recycling. So these are quite not quite a real aspect here, because there are also science behind that, but also there are a lot of things that to consider as well, including the economics and other aspect. Now, I just want to mention here. So yeah, just recently, a couple of months ago, we had the Tokyo 2021 Olympics, right? And I bet you know that the medals that they use, or they prepare for the Olympics, actually coming from end-of-life products, end-of-life materials, end-of-life products, basically. So, for example, here, the approximately about 5,000 medals come from 80,000 tons of recycled electronics. So around 2017, 2019, they collected about 6.2 million used mobile phones, and they extracted about 30 kilogram of gold, 3,500 kilograms of silver, and 2,200 kilogram of bronze. So, so it's coming from this electronic waste. Now, I don't know if you get a chance to see how they make these metals. So for the gold medal, it's actually not pure gold all up to the center. It is actually silver metal, but then they dip it into gold, into liquid gold, and to cover and to coat the surface with gold. Right. So so we've looked at about recycling. So we're going to go into details about recycling in a bit. So I mentioned that earlier, the definition of recycling, that is the reintroduction of recovered materials into the material cycle. Yeah. Now, this basically involves the breaking down of the product itself into separate materials or component, yeah, which can be used to make new items of the same type or a different type. So you can make it into the same application as well, or we can actually use it if you go back enough to go into the basic materials. Of course, we can use it for a different application there. So it's breaking down of each product into separate materials. So like I said earlier, recycling is good, right? But may not be the first option or the first choice. And we can see that from the benefits and from the disadvantages of recycling, and we can decide when to recycle, and also it also helps us to find the weak points of recycling, where to improve, right? So if we look at just from the benefits, right? So it's obvious when we recycle, it reduces the consumption of primary resources, right? And it also means that we reduce the production of waste associated with processing of the primary resources, right? So instead of going back from the beginning, from the Earth's crust, right? We after that, we and including all the process and waste in there, so that's one of the benefits there. So in this case, we will use less ores, right? Primary ores. We will use less petroleum, right? We will cut down fewer trees because of this. Less waste rock from the mining, less CO2 to be produced, so on. and in general also reduce the amount of waste that already formed, right? So so fewer mobile phone waste, fewer magnet waste, fewer solar panels waste, and so on. And the other benefits includes the reduction of the dispersion of toxic elements into environment, right? So some materials such as lead batteries, for example, we don't want them to be, landfill, right? Because it can actually affect the environment, and we want it to be recycled. In fact, lead acid batteries is one of the most recycled. It's 100%, almost 100% return rate. We'll speak about that in a second. And because it's pretty straightforward to recycle lead acid batteries, and now also the system for collecting and recycling these lead acid batteries is also pretty good, and that's just a good example of a good benefit of recycling. Another benefits, less space required for landfill, and also less energy compared to processing primary materials, right? So we're also going to look at that one in more detail in the next few slides. But one thing that I want to emphasize in here, even though we can process things with less energy, there's some energy requirement, for example, for collecting and transporting of these materials back into the plant for processing. Yeah, we'll go into that in a bit later in the next few slides. From the perspective of the disadvantages and limitation, right, there are a number of things as well. So one thing that quite important is the quantities and proportion of materials for recycling may not match the current demands, right? So it could be due to a number of things, including the time lag recycling. Yeah. So the ramification to that is that some materials can be in excess for demand, right? And that can also affect the price of that material, or it can also be not needed anymore because of new technologies. It's not requiring to use that particular materials. So the kind of mismatch of demand can also affect the recycling process, right? Because in the end it's about economic, right? So that's something to think about there. The other thing is the quality of recycled materials may be decreased, right? We will also look at that into more details for different types of materials. There's also possibility of getting impurities, and also getting some trap elements in, let's say, metals, in iron and steel. So for example, tin, and copper, actually tin mainly, is not good in steel. Yeah. So tin is a trap element for steel. So it's very difficult to remove tin from steel, from iron. But the chance of getting tin into steel is high if we use recycled steel, recycled sort of iron. The reason is, for example, fridge. Yeah, contains steel, but there's also the part of fridge that contain tin. It can also be from other sort of source, and that can go into the steel recycling systems, steel sort of loops, recycling loop. And once it goes into the system, it's very difficult to remove. And one of the things that we can do is, of course, to dilute them, but it can be a problem. Yeah, so that's one example. Regarding the quality, for example, a paper fiber, we can actually recycle paper fiber, but each time we recycle them, the quality will be decreased, right? It has something to do with the detailed structures of the fibers itself, which is getting shorter and shorter and shorter, and you cannot get the same quality as the original fibers, right? Now, doing recycling is also produce waste, right? And doing recycling, especially trying to remove impurities, can also result in a longer process chain, right? Like, for example, I mentioned about the tin problem, which means that we have to find another way to remove tin, which will be the new sort of additional process that we need to do, and that can be produce more waste, but also produce energy, or produce waste, but also taking more energy. Recycling can also be expensive because it will involve some collection, transport, separation process, and also processing. And collection and transport can also become quite high, in terms of the costs. And this can be also the showstopper for recycling process. And last one, limitation of recycling is that recycling represents a loss of embodied knowledge as well as embodied energy compared to reuse and remanufacture, right? So I'll explain that in the next slide. What does it mean by embodied knowledge and embodied energy? So basically, design and manufacturing knowledge embedded in a product is lost when it's broken down to its materials, right? So what it means is like, okay, let's get some examples, right? Now, when you design a certain functional materials, right? Let's say, I don't know, let's say rare earth permanent magnets, right? Well, from the perspective of materials, it's basically containing only neodymium, iron, and boron, let's say. The simple rare earth permanent magnet, right? So it's only neodymium, iron, and boron. But for us to make a really good magnet, it undergoes a certain process, certain manufacturing, right? And you sinter them, and then you make sure that the magnetic field is aligned. It's not trivial manufacturing process, right? So if we reuse this material or remanufacture this material, then we can still use that embedded manufacturing knowledge. So we don't go as far back, but if we recycle them, and then we get only back the neodymium, iron, and boron, then of course that process, the complex process that we did, basically lost. So we have to do that again from the beginning to do that same manufacturing process, right? And the same thing that when we do that, we also have energy associated with that. So there's energy embodied with that one. Another example is when we're talking about aluminum. When we make aluminum from alumina, from bauxite, you make alumina. From alumina, you make aluminum. That's quite a long process, especially from alumina to aluminum. Just from the thermodynamic value, from the thermodynamic perspective, to remove oxygen from alumina is quite high, right? And so that process requires chemical energy that's already high. And to do that process industrially, you actually put more than just the chemical energy there to make aluminum. Now, if we go back to get the original materials, in that particular example, we will need to put into the same high energy to get aluminum, right? So there's something in there that is lost, which basically energy, embodied energy, as well as manufacturing manufacturing knowledge, manufacturing process. Right. So basically, reusing and remanufacturing retains a lot of the embedded knowledge and energy, and they require less energy and produce less waste compared to recreating the same products from recycled materials. So that's why in the hierarchy that I mentioned earlier, recycling is not may not be the first choice in doing things in this situation. Okay. Now let's look at in more details about the energy required for recycling different materials. Yeah. I mentioned earlier, recycling, especially reprocessing of particular metals or products or materials, basically, potentially we only use smaller amount of energy compared to processing stuff from the primary production. So this is actually illustrate that one, right? So for example here, when we talk about different types of materials, there's paper, glass, aluminum, sorry, copper, steel, lead, nickel, and zinc. These first two columns showing us the embodied energy in gigajoule per ton when we make these materials through primary production or through secondary production. Yeah. Now I just want to point out in here, let's choose aluminum. If we make aluminum from primary production, from the bauxite, alumina, and then getting aluminum, the embodied energy, the energy that we required to make that happen, to get 1 ton of aluminum, we need to put about 220 gigajoule per ton, right? But if we want to make aluminum from secondary resources or secondary production, for example, remelting of aluminum can or aluminum foil or other source of aluminum from aeroplane or whatever, just for the remelting, we only need about 4 to 20. So it's actually less than 1/10 of the energy required to get the same amount of aluminum per ton, for example. So this is the comparison, between the secondary to primary, right? So in here, you can see that most of this, you can see the energy for recycling is much compared to the energy for primary production. So the aluminum one is about 10 times smaller, right? Or 10%, right? 5 to 10% of the primary energy production. Now the steel slightly bigger, 20 to 40%, but still is pretty good, compared to for processing from the ore, for example. Zinc, for example, yeah, to recycle zinc. Also have a similar sort of reduction in energy with steel, but in here with glass, right? If we can just remelt glass as opposed to making new glass from primary ore, that is a bit of high, in this case, on a small fraction of the energy for primary production is used. We use secondary production there. Now, however, I should mention that in here, even though it's only 1/10, a quarter, and so on, even half, right? But there are other sort of costs associated with doing that, right? So this value do not include the energy for collection, transportation, for example, and additional pre-processing, separation, and stuff like that, which can also be quite expensive if we're not really careful, right? So it actually can become higher even, and it can be showstopper as well. Right. So now it's roughly already 1 hour. So I just want to give a few minutes if you have any questions or if you have any comments before I continue these materials further. Do you have any comments or questions?
Okay, everyone, do you have any questions?
No question?
Not yet? Right, okay. If you
Okay.
have any question, you can also write it on the chat, yeah? And then,
Yeah.
of course, we're gonna read it, and then Professor Akbar will be happy to answer it. Okay, maybe please
Okay.
continue first.
Okay, I'll continue again.
Yeah.
So, right, I'll share it again, and then we go back to this. Yeah, so I mentioned a bit about return rate earlier. So I think it's also good for us to sort of look at that one as well in terms of some of the terms that we often use when we talk about recycling, right? There is what is called recovery rate, right? So recycling rate, return rate. So you will often hear this term, right? So what are they? Now, recovery rate. So recovery rate is basically the amount of material that is recovered by a collection system as a percentage of the material available, right? So it's only about recovery of the particular material compared to the available material in the system. Yeah. So if in the world we have about 100 kilograms of mobile phone waste, for example, and then that's scattered around the world, and then in our plant we have only 50 kilogram of this mobile phone waste, means that the recovery rate is 50%, right? So it's just recovering that material itself. There is also recycling rate, right? So in recycling rate, it is actually the amount of material that is recycled as a percentage of the quantity of the material available, right? So from that 100 kilogram, right, we can have about 50 kilogram recovered, right? All of this 50 kilogram actually recycled. And let's say only half of that, 25 kilogram, is recycled. So that is the recycling rate, 25%, right? So the amount that is recycled to the amount of the available material. There's also return rate. Now, this is slightly different than recovery rate and recycling rate because it's a different perspective here. So the return rate is basically the percentage of a particular material that is supplied from recycled sources compared to the materials that is produced from the primary sources, right? So we can say something like, okay, we have a product, I don't know, like paper. Now let's say the existing paper around the world is 100 kilogram, right? And let's say 75% of that made from primary sources and 25% is made from recycled sources. In that situation, the return rate of that paper is 25%, right? So of all the existing materials, the percentage or the portion that is coming from recycled sources represent the return rate of that particular material. Right? So yeah, recycling rate and recovery rate, in a way, like I said earlier, is connected, but not with the return rate in here. So if we look at here, the recycling rate is always less than the recovery rate, because not all materials actually recycle. And even if we try to recycle everything, there also may be some material losses during the processing as well. So it's good if its recycling rate can close to the recovery rate, but in practice, it's quite difficult. Now, these are some of the numbers of the recovery rate, recycling rate, and return rate from different types of simple materials. We can look at here a number of examples. So we can look at lead in the USA, right? So the recovery rate is higher than 80%, right? So which it means of all the lead that is currently used in America, right? 80% of those lead actually produced from recycled materials, right? And only 20% is coming from the original primary source, which is quite amazing, isn't it? So of all the existing lead in the USA, 80% actually coming from recycled lead. And the recycling rate is pretty high. It's 80% to 90%, right? Oh, I'm sorry, that one I mixed. I was talking about a return rate, yeah? So let me correct that one, I'm sorry. So remember, return rate is the ratio of the amount of recycled, the amount of materials that coming from recycled materials and coming from the primary recycled. So I'm sorry, it is actually 50%, more than 50, not 80%. So more than 50% of the lead in USA is actually coming from recycled lead. Recovery rate and recycling rate. Recovery rate is larger than 80%. So recovery rate means that we collected, available lead of the amount 80% in the USA. And of that, right, we've got about 80% to 90% recycling rate, which is also quite high. So that's a good example of high return rate and high recycling rate of metals. We can also see here that steel, for example, and we think about around the world. Let's look at application of steel in machinery, and the location is around the world. Now the recovery rate is 95%, and the recycling rate is 90%. So it is actually pretty high, yeah, even higher than this lead. So you can see from here that lead and steel have very high recycling rates. So my question is why? Can anybody explain to me why lead and steel have very high recycling rates? I heard from Buvini earlier. There's a student called Akbar, same name as me, Akbar. Akbar, do you know why lead and steel have very high recycling rates?
Sorry, sir, no idea.
Can you hear, or you don't know why? The other students, do you have any idea why lead and steel have very high recycling rates? Come on, guys.
Because it is easy to be recycled, maybe.
It's easy to be recycled. The process itself, that's one of the things that's good. Any other comments or answer? So thanks, Ignatius. That's pretty good. Yeah.
Because it is really easy to get the material. I mean, like for steel, it's often that steel is used to make the main component of something, like cars is the body of the car, or if in the construction it is made the main part of the construction, so the part is big. So when it is want to be recycled, yeah, just take it. Like if other things that is part of something, it is really hard to recover because it is part of something, but still is mainly produced to be the main body of product, so it is easy to collect, to recover it.
That's also good, Rashid. So basically, Ignatius and Rashid raised two good sort of rationale. Lead and steel have a very high recycling rate. So let's elaborate those two answers. First of all, easy of recycling. So that is correct. So for example, in steel, one major way to recycle steel is remelting them in electric arc furnace. We will discuss about this in more details later on, maybe in the second week here, where we go into more details about the metallurgy process. Right? So that steel in general, when we recycle it, is pretty straightforward process. Aluminium as well is only remelting. Right? We may do a bit of adjustment, adding some alloys or removing a bit of impurities, but the process is quite simple. It's remelting them, as well as the lead. I mentioned earlier the main one of the main sort of use of lead is for lead acid batteries. Now, recycling of lead from lead acid batteries is pretty simple. It's also just remelt them in a heating furnace, in a melting furnace. So the actual process is quite simple. Now, second, Rashid also mentioned about easy to get. That's also correct. He mentioned about some of the component, particularly in here, let's say for the machinery and construction, why the recovery rate and recycling rate is pretty big. First is, of course, some of these parts are also big, steel frame or steel structure. So when you try to collect them, but you collect more, right? So you actually have easy to collect them. But also some of these metals, lead and steel, now this is number 3, they also already have quite a good recycling cycle, route, right? For example, construction company, especially let's say automotive company, know for sure, okay, it's coming from the steel, coming from the car, then know where to find them, and then they can get and get back from the scrap yard. So all that system already in place, so that it will be easy to get back and to be processed back. So that's some of the reason why some of the metals actually has high recovery rate and also high recycling rate. Right. So now let's go. Think about a bit more complexity about the recycling in terms of the economy. Yeah. Now let's start with something simple here. This is energy required for processing of recovered materials. Now remember, in a few slides before, to process aluminum, to remelt aluminum is only 1/10 of energy required than the processing from primary sources. So we can construct a graph something like this, where the bottom one, the x-axis rate, So let's say the return rate 40% means that 40% of the existing materials is made from recycled materials, and the 60% coming from the origin virgin materials or the primary ores, right? 100% return rate means that everything that we have on the market is coming from recycled materials. Now, in here, the y-axis is the energy requirement in each material. Okay. So if the material exists on the market 100% coming from primary ore, then we have this quite high energy, right, which is up there. And if we have 100% of materials coming from recycled materials, then we have something in here, which is about 1/10, or in this case 1/6 or whatever, or 1/7. So this is just speaking about energy for primary production or energy for reprocessing, right? So at any point, at any value of return rate, then the total energy will be just the add of the two. Let's say at 40% in here, so energy for reprocessing of 40% of the materials, that's probably, you know, that one there, a couple of, you know, this is arbitrary, but then if for primary production is up there, so the total will be this red line here. So on the system, the total energy for processing is just the sum of the two, and it follows this straight line, this straight red line here, right? So that makes sense. So from this perspective only, it is good if we go for high return rate, right? Now, let's look at the other aspect of things. Previously, Rashid mentioned about easy for collection, right? That's good, because if it's not easy for collection, what happened is this one here. So we still have that the for energy for primary production and also energy for processing for pre-processing. But you know, if we want to get a higher return rate, let's say up to 100, means that we need to get more energy to get this materials into, or recycled materials into the plant for processing, right? And that increase in energy for collection and sorting actually increase quite exponentially, right? So as you can see here, as the return rate increases, now the proportion of available material to be collected and sorted increases. And the quality or grade of this material collected also decreases. And the distance of transport become longer, and all of this result in the increase in the energy for doing that, for collection and also sorting of these materials, right? So that's sort of the line there. So basically, the complete picture is we also have to add this aspect. So this is actually the complete picture here. So so this red line here is the total energy for production of the material, which also include the collection and sorting and or pre-processing. Yeah. So as you go towards 100% return rate, it becomes quite economically not feasible to do that, right? So we want to go something around here, right? Where, okay, we have, you know, a good sort of proportion or good return rate where we can minimize the production of, in this case, energy, but it relates also to overall economic of the process. Yeah. So in conclusion, recycling of materials is quite less energy than primary production until a return rate is reached where collection and sorting become the contribution, the higher contribution of costs, right? And when that happens, then the process of recycling become not economical, and it becomes unfeasible, basically. So in a way, 100% return rate may never be economically feasible, unless, of course, a particular intervention is applied into that. Yeah. Right. So so that's basically the general aspect of recycling there. Now, what I want to do is starting to go into details about the recycling in recycling, right? So when we talk about complex product, yeah, it can be cars, you know, consumer goods such as electronics, and other sort of complex products. Yeah, it can be anything that contain many different parts, many different materials, and so on. Now, the general process, the general step is basically 3 steps. One is, the collection itself, right? So that's the first step. We mentioned a bit about the collection. Second is the pre-processing, right? Which consists of liberation and separation. I will explain about this in this slide and the next couple of slides. And of course, the last bit is the metallurgical processes. This is where also the context of this unit, the process metallurgy, how process metallurgy can play a significant role or important role in helping to do this. Yeah. So so the pre-processing, the approach that we take usually is first we liberate, then we separate, right? So this is applicable to all these different complex products, right? So first we liberate them, second then we separate them. Now, how do we liberate them, right? Now, liberate them can be manually using your hand. You just separate, what we call it. We liberate them, different parts of different, in the product, right? Manually, but what we usually do is, we choose the more automatic way, the more sort of faster way. So the way we do that is by size reduction, crushing, grinding, to make this size of this product into smaller size, right? So for example, here on the right we have a component that consists of 2 materials, the black materials and also the white materials, yeah, as an example. So first we crush them into this mid size, and some of them already liberated, white stuff with white stuff and black stuff with black stuff, right? But then some of them still have a mixture of white and black. We can further reduce the size by grinding, for example. After crushing we do grinding, or make it more smaller. And what happened is we liberate more individual materials, so more white particles separate by itself, and also more black materials by itself, and so on, right? So in here then we do the separation. So that's the next step. So in the separation, we want to separate all the black one. We also want to separate all the white one. There are some unseparated materials due to whether still have a mixture of white and black, or because it's basically just too small or still attached to some fragments, we cannot really separate that into white or black, right? So so that's the process. Liberate, then separate. After that one, it's metallurgical processes. Sounds easy, but in practice, it's not that easy. Of course, this is where all the aspect of mineral processing metallurgical processing also comes into play. Yeah. Now, just a few comments in here. It is actually very difficult and next to impossible to achieve 100% liberation, right? So this is showing that example. Let's say if you have a component or product consisting of two materials, black and white, or in this case, gray and white, that's one by one. Now let's do a systematic liberation. If we reduce the size by 1 millimeter by 1 millimeter, right? So we like cut in this case is a nice one, just to make it simple. As you can see from here, we have quite a liberated gray materials, which is on there, right? On the corner there, sorry, on just in this corner here, right? And that corner there, we have a bit of white over there and white over there. But the rest, is basically a mixture of gray and white, even though in this sort of edges here as well, there's a mix of white and gray, right? So in this particular case, only a very small amount of particles liberated, right? Okay, we can go into a much smaller size of sizing of grinding and milling, for example. So in this case, let's go down to 0.5 to 0.5. So in here, we get more, white materials and also black materials, gray materials. So the one on the corner there, that one as well, this one as well, that one, and you get the white one here, in the corner here. So we get more, a bit more, but the one in the center, for example, here, we still also get some mixture. So if we do this, we can get about 12.5% of white and black material are liberated, but in general, 75% of the material is still not liberated. Yeah, you will need to go to much further size. Then you can increase the liberation percentage, yeah, the degree of liberation there. So even with that small reduction in size, there are also other aspects that need to be considered. That is the cost of making that very small, because if you remember from mineral processing perspective, making the size quite small, it actually the cost to do that increase exponentially as well. Yeah, the higher the smaller the particles that you want to go for, you want to target, the price, the cost to do that is actually increased exponentially. So it's not a trivial matter. So then we can actually construct a graph to look at the correlation between the recovery with the grade. So for any particular average particle size, right, as the target, right, we have this correlation here. The higher the recovery of material, the lower is the grade of a product. That is, what does it mean by lower grade? It means that the product contains more unliberated materials. So that illustrates this sort of relationship, right? So if you want to get for a certain particular size, if you want to get a high grade coming this way, right, then the recovery rate will be quite small. So the number of the materials that quite separated, quite liberated, yeah, with high grade, high percentage, yeah, 100%, let's say that one there, then the recovery rate in general will be small. Right? So we can actually make this, if we play with the size, we can then alter this, right? So if we make it smaller, then we shift the curve actually up, right? So we're decreasing the liberation size as we go that way. So as average particle size is decreased by further grinding or by further milling, the percent recovery of material at any particle grade is also increased, right? That is, we can get more product that contains more liberate materials, but the caveat to that is the energy cost increases, right? So it is about the economic consideration, right? So what do we want? Do we want to have a grade, or do you want to have recovery? Do you want to maximize recovery, or do you want to maximize grade? It's all about the economic of doing this. Right? If it's quite, if the driving force is about high purity, of course, and you can sell the high purity materials much higher in terms of the price, then we go for the grade, and we don't really concern about the recovery there. So yeah. So an example of that is e-waste, waste PCB, right? We will see that one in more details next week, but this is started to go into the details of types of products here. So yeah, so when we talk about waste PCB, you know, looking at that materials there, you know, there are many components, and that components basically quite small. Some of that components only thin layer of, let's say, copper thin layer, or gold thin layer, or silver thin layer is very small amount. And so it's something that very difficult to do 100% liberation for these types of complex product, right? So we need to find a way, some treatment where we, or some process where we can handle multiple elements, multiple materials, and metallurgical processes such as pyrometallurgy in combination with hydrometallurgy can be a way to go to deal with this one. Yeah, so we will discuss that in more detail later. Now, before we go into that complex one, I'll just, you know, so we can start with something a little bit simpler, even though it's still complex. So let's talk about cars recycling. Yeah, so cars contains about 60% steel, you know, 2% zinc, copper, lead, 9% plastics, and there's a bit about fluids coming from, you know, the batteries, or from other you know, the oil and stuff. So how we recycle cars, the same concept applies. Of course, we collect them. We get the used car, we get end-of-life cars. Then the process is, first we liberate, then separate. Then the next step is the metallurgical process. Yeah. So liberate. So how do we liberate? Oops, what did I do? Just coming back. Oh, okay. We got video here. So, well, one way to liberate is using what's called a car shredder. So there are not a lot of video, YouTube video for this one. So, but I'll just try if I can sort of do the video here. Oh, okay. So let's just look at this. So basically, the whole car goes into the universal shredder.
We actually can't hear the sound.
Oh, yeah, yeah.
Oh, just the picture, yeah.
Yeah. Sorry about that. Yeah, I should have set it up for Yeah. Anyway, you can see the image. So basically, yeah, it's about first liberation, then separation. You can see from there, the whole car goes into the shredder. Usually they separate the wheel first, and then of course the lead acid batteries. Yeah, so at least that one, and also the glass that can be separated easily. But then the rest is just go into the shredder, and after that it goes into the next step, which is separation, and then after that metallurgical processes. Yeah. So okay, so now what's the next step in the separation process? So there are different types of separation processes. You usually you probably already seen this one as well from the perspective of mineral processing. Here is some examples of separating light particles from heavy particles, which is based on density. So for example, here we have this air cyclone where we have incoming inlet here, where it goes down through this cyclone, forming this descending vortex. So that's sort of the heavier materials. And at the same time here, the smaller particles, the lighter particles, also moving up following this ascending vortex, and it's actually separated as well from this mixture here. There's also air classifier, where we have a set mix density of feed, but then we provide air blower, and of course the heavier material will also get pushed, but it push only shorter, while the lighter materials will push higher, longer. So it will separate based on that, and you can get separated heavy materials and light materials. And of course, you cannot really have quite a 100% separation as well, because things can also still get stuck and then goes into the different stream there. The next step is other ways of separating the particles based on size difference. It's basically like a sieving machine, and there's a vibrating screen. There's also a rotating trommel screen, right? So in here on the left, basically on the top, it has quite a big opening. So the particles that's smaller than that will go down, and at the bottom there's also a lower opening, and the smaller to that will also go down. And in here the process is similar to that. It's just in here, instead of vibrating, you actually rotate them so that it goes through this different size of hole here. The oversized material will end up at the end, and smaller as it goes down and to be collected separately. There's also separating of particle based on magnetic properties. If it's a fully magnetic, such as steel or iron, then we can use this magnetic separator. So there's a drum magnetic separator where you have magnets inside, and it's rotating. Now the one that is susceptible, that can attract to magnetic field, it will stick until the end here. That's the red one. And there's a stopper. There's a separator there, where it actually remove the magnetic materials from this drum here, and then it's separating. The non-magnetic one is just go through further away, and this will separate this red and the yellow here. There's also eddy current separator. It can be used to separate different non-ferrous metals from non-metals, glass, plastic, rubber, and so on. So the non-metal will be sort of affected or not affected by the eddy current, while the metallic sort of fractions have some effect when we apply this eddy current, and it will sort of jump, or it will separate it into further sort of section there. So the picture on the bottom there is showing something like that. So these are just some limited examples. There are so different ways of separating this, which based on sensors, based on lights, based on the actual composition as well, right? So some highly sophisticated machine, expensive machine can do that. You have this quick X-ray, XRF detector as well, that can be used in addition to other sort of separation technique. Yeah. So this is I show you the current flow sheet for modern car recycling plant, right? So you've got this whole car, and then first there's a selective dismantling. There's some tires, batteries, like I said earlier, liquids, they're separated first. Some of the material that can be reused, for example, bumpers or whatever, or steering wheel that can be reused or whatever, it's also separated. And then it just goes into Saturator, like I showed you earlier. Then you get air cyclone to separate the fluff. There's also magnetic separator, I showed you earlier. We use thermal screen to screen different size of materials. Some of the fraction go to eddy current processing to get the non-ferrous mix, and the remaining go to landfill. It also combines, manual. So there's a hand sorting, but the magnetic separation separate the magnetic part in the steel, for example. But from the trommel itself, we also can separate further the light plastic, rubber, and metal foil with the heavier rubber, plastics, and other stuff, wood and magnesium, and then also goes into further heavy medium separator or further eddy current separator. So in here, for example, we get some of the aluminum, some of the stones which not recovered previously, that goes into landfill, and also some of the non-ferrous mix can also be separated if it's at all possible. If you have separate, zinc, copper, lead, and so on. If not, they comes as a mix of non-ferrous metal as well that can be processed further. Right. So, and also about e-waste. So this is also another quite complex material, right? So e-waste, some people also call it WE. So it's waste of electrical and electronic equipment, right? So it is electrical or electronic equipment which is waste, including all components, sub-assemblies, and consumables, which are part of product at the time it's studied, right? So that's the definition from European WE directive. There's also slightly different definition from Basel Action Network. E-waste, it encompasses a broad growing range of electronic devices, ranging from large household devices such as refrigerators, air conditioners, cell phones, personal stereos, consumer electronics, and computers, which has been discarded by their users. So it's actually quite a range of materials there, right? So why we want to process e-waste? So previously, of course, there's a in the context of silicon and efficiency, of we want to process this one because electronic waste actually can be it contains quite a many metals, many elements. It contains precious elements, platinum group elements, base metals, hazardous metals, and rare metals. So it's an opportunities, but also challenges, because we will need to be able to handle the hazardous elements. But if we do it quickly, we can also take the advantage of of the economic value inside the e-waste there. So there are currently about 50 million tons of e-waste generated annually, right, globally, and only about 10% to 15% actually recycled. So we want to increase that recycling rate much higher. Right? So yeah. So in the context of circular economy and resource efficiency, why we process e-waste? First, of course, because there's a decrease in the concentration of the grade of the ores around the world, right? But like I said, this e-waste is actually alternative resources for these metals. So just to give you some ideas of the things inside e-waste. So when you see a wedding ring, such as a shown in here, it may contain up to 2 grams of silver, right? Sorry, gold, aurum. And these 2 grams of gold can be obtained from only 15 kilograms of waste PCB inside the mobile phone waste, right? But if we want to get this same amount from underground, we have to process about half a ton to 1 ton of ore, right? So as you can see, it's only it makes sense if we're able to process this mobile phone waste, because it's only 15 kilograms already above ground, as opposed to processing from the original ores underground. Yeah, and to give you the same ideas, 1 ton of mobile phone waste contain about 200 grams of gold, 3 kilograms of silver, 100 kilograms of copper, 100 grams of palladium, right? So that's just the thing that I selected there. There are more than that. You can actually get more than that. Right. So just to give you some more illustration here. Now, if we look at, so this table shows us the distribution of elements or materials within the e-waste, different types of e-waste, right? And selected metals. So let's say if we look at mobile phone, yeah, in terms of weight, so we look at this top table here, 56% of mobile phone basically, could be plastics, right? This is some of the earlier mobile phones here, and 13% of that is copper, 5% is iron, 1% is aluminum. Now we also have gold, silver, and palladium, which is at ppm level. But when we want to look at this in a different way, in terms of the values there, share, so you can see from here, the same mobile phone, about 93% of the value lies within this gold, silver, and palladium. So this one here, and copper is only about 7%, and we don't actually value the iron and aluminum in the mobile phone. So we want to actually be able to utilize this and then recover this value back for us. Yeah. So now it's 15 minutes towards 7 o'clock. So I may not be able to finish this today, but I can finish this by next week. But I just would like to give opportunity if there are any questions or comments or anything.
Right. Thank you very much, Professor Akbar. And okay, questions from students? Okay. How about Nurul and Akbar ask questions? This morning we have a meeting about our plant design, and there should be a lot of questions from you. Nurul? Akbar?
It could be
Akbar not
anything.
here ya. Oh ya, itu. Oke, Dozi.
Thank you, Pak Akbar and Winnie for the presentation and for the material. Maybe I have just searched in the internet that it showed that the e-waste treatment and in general case the metal processing industry in Australia have grown throughout the times, and especially in e-waste. Also, I searched in the internet, and it showed that the market size and the production scale is still increasing from year to year. What is actually the main cause of this the fast-growing market of Australian e-waste market? It is because of the technology maturity, or is there any additional support from the government, or other cases that really support the e-waste, the growing of e-waste in Australia? Thank you.
Thanks, Dozy, for the question. So I'll probably just answer that before any other question. So your observation is actually correct. So maybe I just want to tell you further back, a couple steps back. So I should mention Australia is very strong in minerals processing and metals processing, and also technology for mineral processing as well as metallurgical processing. So I should mention the current technology that is used for e-waste processing around the world. A lot of them, some of the big portion of them actually developed in Australia. So, for example, you're probably aware the taupe submerged lens technology, TSL technology, that was actually developed in Australia, and that is used in many smelters, especially copper and lead smelters around the world. And this technology is actually used for processing of e-waste as part of processing of base metals in that particular smelter plant, right? So that's actually Australia, one of the Australian technology, that TSL, but now only bought by a Finnish company, but the original technology is coming from Australia. Actually developed at CSIRO, which is quite close from Swinburne here. So now around, let's say, 10 years ago, even before 10 years, this technology has existed, right? But in the last 10 years, actually, Australia is a little bit behind. So we sell the technology, and then it's used around the world to do this recycling and e-waste processing. But in the past 10 years, we actually a bit behind. But then, of course, there's a lot of drive inside Australia, including there's this not new at that time, it was new. There's this collaboration between a number of universities, including CSIROs, that is a cluster-less wealth from waste funded by the government, to try to find out why this recycling of e-waste in Australia is not really happening while we have that technology. So we tried to do that study. It's a multidisciplinary study that look at what is the, I was also part of that sort of consortium. So we're trying to find out what is the best way to do that in Australia, the process route, and also the geographical aspect, the socio-economic aspect, and other stuff. So then, we also advise the government to them of our finding, and on how the best way to increase the recycling of metals in Australia. And that actually get some effect, right? So the government started to listen and also try to understand the importance of doing this in country. Previously, what we did was just send all this e-waste outside Australia, right? So there has been a lot of push since 5 years back towards processing of e-waste in Australia, and government put some funding for research. Government put also some sort of incentive for the industries to do that in Australia. So you can see that slowly it's increasing the uptake of metal recycling in Australia. And also recently, about 2 years ago, or 1 year, 2 years ago, also in China and also Asian countries, they sort of realize they don't want to get the waste from Western countries and also including Australians. So China, for example, they ban the import of waste from Western countries, including Australia. Then, of course, Indonesia did the same thing. Malaysia did the same thing. And other sort of Asian countries did the same thing, which means, these waste have to be processed within Australia. And that also accelerate as well the uptake of e-waste processing in Australia. It's not done yet because it's still small on a smaller amount, but it's increased from before. So it's a good progress. I think the problem now is the collection system. So there's a national collection system called NPCRS. We collected quite a number of e-waste, but still not enough because there are still a lot of e-waste that are not collected yet. But it's getting better and better. So I believe in Indonesia also similar things happening there. So and the potential in Indonesia also pretty big, right? So I have a students currently looking at the potential of e-waste value in Indonesia and estimated that currently about 2 million tons of e-waste, just waste PCB, generated in Indonesia annually, and that will increase significantly in the next 10 years. So yeah, so I hope that that's a long answer, but I just thought I should mention the whole story there.
Okay, thank you. Right. Any other questions?
Thank you, Pak.
Okay. If there's not a question, I would like to ask questions. About the e-waste. About the e-waste, is it valued? For example, if we give e-waste to the collection depot, and then we can get money from that one, the consumer, or what it should be like?
Yeah, so that's a good question, Ibu Winnie, and I think that's also one of the problems as well in Australia and also around the world. So at the moment, the waste PCB is not valued. So, but the collection companies actually in Melbourne, in Australia, knows the value of this waste PCB, right? But the problem is there's no standard of what's the price of this commodity because it's not considered as a commodity. It's just waste, right? So, I've been approached by sort of a number of companies saying, what can we do in this area? Because there's no standard about the value of waste PCB. Is one thing, and if we want to price them, what is the suitable price? And also the problem is that waste PCB. I should explain that in the next few slides, but I'll explain that next week. The composition or the concentration of the gold and silver, this is an average, but from one product to another product may differ significantly. From one time to another time may also be different. Like for example, these days, the amount of gold in waste PCB is actually less than 100 ppm because the other elements exist in there, but in 10 years ago it can be up to 300 ppm. So the price also, we don't know how to put the price there. When we want to analyze that one, also the sampling is difficult because it's very different. So it is still a problem at the moment. There's still no solution to that, but just in practice, Australia currently is not really valued. I want to buy that PCB of this. It's still like, for example, if I want to put my mobile phone away, I don't have to pay, of course, but I don't also receive any incentive when I get paid on that one. So yeah, so that's the situation at the moment.
Okay, thank you very much for your question. Okay, any other questions, students? or in Indonesia also is fine. No questions? Okay.
It can also be any other topic as well. If
Another
you have
topic,
any
okay.
question, that's also fine.
Yeah.
As long as it's related to process methodology.
Right. Okay. I think yeah, the time's almost up as well, so I think we can conclude the lecture for now. It is general, but really giving us an idea. Yeah, and it's quite similar with the physical processing of ores. Yeah.
Exactly.
So
Yeah.
we have that one with the Hayes books. Yeah, few weeks
Yes.
ago. So, but maybe the difference would be about the sorting, the collection, the dismantling, and also I think there's a shredder. Yeah, that because we only know crushing and grinding, but in the cars, that ductile materials, it should be shredding. Yeah, berbeda. Okay. Right. Okay. So I think that's all for today. Thank you very much for all of your attention. Let's open your camera and then have a picture together. I need this for the. Okay. Thank you very much. And then next week we're still gonna continue with more exciting presentation and also more detail. Yeah, Professor Akbar. Yeah, I think with more detail examples would be very useful. Okay. Siap ya semua ya? Okay. 1, 2, 3. Okay. Right. Okay, thank you everyone. Terima kasih semuanya. We're gonna see you again next week. Thank you Professor Akbar, and we're gonna see you next week as well. Bye-bye.
Thank you. Thank you, Bu Winnie. Thank you, everybody. So I'll see you next week, and have a nice weekdays, and keep safe, everyone.
Okay, thank you.